Alright, we'll chat here. Good morning. Hopefully, this starts. Codeforces still says we're offline. There we go. Welcome. Okay. Let's go to YouTube so we can see the comments. Good morning, everybody. Hope you had a good contest. Ideally, a better contest than us. We'll wait till we get some good mornings here before we start. And I guess maybe we'll bring up the problems. How was your contest for those of you who participated? Hi, Govind, Nikhil, hey, how's it going? How was your contest, guys? How'd you do? A, B, and C. That's pretty good. That's as good as I did. I had some issues on D. Mainly just math issues. Lots of math, right? Hey, Rock. What a name.
Rock.
Yeah. Wait, Blake. We know Blake, right?
Oh, it's Blake. Hey, Blake. Nice. I got MB.
Is Blake go to UCF?
Yeah, he's on Dev.
Hey, Blake. Watching both streams. Someone's doing that again. That's like a very impressive thing to do. Well done. You have to have a good talent to be able to hear two conversations at once. Comprehend both of them. And be welcome, Piyush. How's it going? Alright, we're going to start here then. If people miss out on A, I don't think it's too big of an issue, because A is pretty easy.
Yeah.
Alright, so there's this nice, first of all, shout out to whatever authors made the 3 blue, 1 brown animations. They look really slick. The only problem is they don't load in the beginning of the contest when Codeforces is getting DDoSed. So someone's got to figure something out. Maybe that's a talk to Mike issue. But yeah. Anyway. Yeah, I guess let's talk about C was greedy. That's a hot take.
C was greedy.
C was greedy?
Well,
you say so. I don't see it, but alright, let's talk about A. So you've got a robot. Let's hang on let's just, someone else has done the work for us, right? So you've got a perfect animation, check it out. And in this animation, make sure the volume's off. Yeah, in this animation you've got a robot, starts at some position, and then it's going to move around, but the way it moves is very limited. The dx and dy are always plus or minus 1. So it's always moving like 1 square diagonally from where it starts. And then it'll move, and then it'll kind of bounce off a wall. And it'll clean all squares in its row and column, which is a bit unusual, but just how the problem's defined. And you stop when the row or column matches the star, or the dirty space. So Thomas, what is the approach you used for this?
So you can do it both in the X and Y separately, and then, you know how far it has to travel. It either has to go up to the dirty spot, or right, or it has to go bounce off the wall and then up, or bounce off the other wall and then go right, or something like that. So it's either going to go directly to it, or to the wall, back to itself, and then directly to it.
Yeah, so basically you can look at each dimension separately, because one of the dimensions will be the constraining factor. So within a dimension, you start at some position and then you're going towards some other position. So let's say you start at the smiley face, then you'll go like this, or it'll be like this, and then you'll just hit the X. So those are the two cases.
Yeah.
So pretty easy. That's problem A. Sounds good. Let's talk about problem B then. Game on ranges. Yeah, so this one probably has lots of different approaches, although I imagine most people use the same approach I did just because it was so easy.
Yeah.
So in this problem you've got what happened was you had some big range of a bunch of elements. Like this, maybe. And then Alice has the range, or I guess you have a bunch of sets of ranges. And then Bob will like pick one element and erase one. And then Alice will say like, okay, now pick this set. And then Bob will pick and erase one of the elements in this set. And then Alice might say, okay, now pick this set. And then Bob picks maybe this middle one and erases it. But he can pick anyone he wants. And then keep going till everything's disappeared. So at the end you have like some sort of tree, basically, of the ranges with the things that were deleted in it. So initially you've got like the entire range. And then this gets split up into like two separate ranges. So you've got like this one here, and then this one here. And then each of these,
It's like bigger.
let's draw it better. Like this and this. So you kind of have like a segment tree, but not necessarily balanced. Or it's like maybe a binary search tree is the best way to describe it.
Yeah.
Like when you do binary search, you know this isn't the answer. Then it's like you have this half and this half. But your binary search just isn't splitting in the middle.
Yeah.
So how'd you do it?
So, you can sort by like range, like the distance of the range.
By size?
Yeah, size of the range. And then I used a segment tree to find. So every time I would find the answer. So you start off with like ranges of 1.
What is the answer?
Or sorry.
Oh, I guess we should just. So what you're looking for is like, for each range Alice gives you, they're not necessarily in the given order. You want to find which point Bob split it at.
So you start with like the smallest ranges, so like the ranges of 1, and I have a segment tree, and the segment tree, each element would be filled with its index, and then the ranges of 1, you just find it, and then you would set, once you found the answer to that given range, you would set it to 0. So then if you did have some given range, the only things in it would be a bunch of zeros and then the answer, because everything else would have already been set to 0.
The only things
inside of that range.
Yeah.
And then I just call a max query on that range.
Yeah, that works. That works. Yeah. You don't really need a segment tree though, like because you know there's only going to be one thing in the range at all times.
Yeah, I didn't know how to I didn't want to do like an end search every time.
You just use a tree set.
Yeah, you could.
So you just have a tree set. Just do next higher from the left.
Yeah. Oh, that makes sense. Sure.
In particular, I guess we can just show what the code looks like for that. I thought I had a pretty clean implementation. So, in particular, yeah, you just have each of these ranges, which I sort by size, and then this is the entire problem. So we sort the ranges, and then we go through the ranges from smallest to biggest. And the answer for a given range is just the first thing in the tree set after the left bound of the range. So in C++, instead of doing ceiling that doesn't have ceiling, you do lower bound, and then you'd have to remove it from the set as well in C++.
So the higher bound doesn't even matter?
Yeah, well, it matters for sorting the ranges.
Oh, sure, yeah.
But after that, it's irrelevant.
That's pretty cool.
So, yeah, all right, that's a thing.
I was using your segment tree from the hack pack. And
my segment tree template?
Yeah, well, and I was using set instead of update.
What is set? What's the difference?
Set is a method that's implemented inside of the class that you're not supposed to call.
Was it like some faster version of the segment tree?
It was like you had like delta min max arrays or something.
I don't know what you're talking about.
Oh, well,
anyway.
Used my segment tree around for like 20 minutes and I finally fixed it.
Yeah, sounds good.
Yeah.
All right, so then we'll talk about problem C as well. We're not going to get to E here because we haven't even read it, but we'll talk about C for sure. So C was balanced stone heaps. We have n heaps of stones. The ith heap has this many stones, and we can do some operations to like move stones earlier in the array. So maybe we'll do some example here. Do you have a good sample, Thomas, that you remember?
I liked the first one's pretty good.
Okay.
I liked the first one.
So you've got, initially we've got 1, 2, 10, and 100. And what we can do on a given turn is we're gonna go this way, iterate through this way. And you can take any multiple of 3, put a third of the stones in the place before us, and then the other 2/3 in the thing before that. So in this case, you take all 9, right?
Yeah.
So okay, so you take 9. So you do -9 plus 3 plus 6.
Yeah.
And then we have this 100. So for the 100, we would do like -66 or something.
It's like 18.
And you -60. Should be fine.
Yeah, you can do whatever.
So -60, this will give us
10.
20 plus 20.
20.
This is plus 40.
Wait. Oh, yeah.
So in particular, yeah. So like 1/3 of these things go here, 2/3 go here. So then after we do these operations, we're left with 7, some big number.
45.
45.
21.
21. 40. And 40.
Yeah.
So we want to maximize the smallest. In this case, the smallest is this 7. So Java running in the family. Yeah, I think part of that is Java running in the family of UCF programming team.
Yeah.
But Java in the Harmeyer household as well. Yeah. So we want to maximize this. The question is, how do we do it? And the answer is, well, I mean, do you have any ideas?
I didn't solve it.
But yeah, Thomas didn't get it.
Yeah.
Seems pretty clear to me it's binary searchable, right? So if we can make it at least 5, then we can make it at least 4.
Yeah, so I tried binary searching, although my implementation for whether or not something was possible must have been wrong. What I did was...
Refilling samples?
No.
You're passing
I
samples,
was
but got it
passing
wrong.
samples but got it wrong
I
on
see.
pretest 2. So what I did was I said like, I tried 2 different things. Try and give, like, only care about 2 below you and then run through, and then only care about 1 below you and then run through, and then...
When you say only care about 2 below you.
So for like 10, check 1.
Oh, like
and then
the
100,
restriction
check
based on
2.
this. Yeah.
And then you'll go through that, and then you'll do another for loop where you'll have 10, check 2, and you'll have 100, check 10.
In both of those situations, though, you're making decisions that, like, could be wrong.
Yeah, so that didn't work.
Yeah, so I think that's the root of your problem.
And then I started to go, I didn't finish this implementation, but then I started to go backwards, and I was like, oh, if I'm at some index, you should choose whether or not, like which one or 2 ahead of you should take from.
How do you do this choice?
I don't know.
Yeah,
That was
so
my issue.
you've got like lots. The array is big, right?
Yeah.
I don't know, 10 to the 5th or something.
Yeah.
Yeah, 2 times 10 to the 2 times 10 to the 5th. So since it's big, you have to make a lot of choices, which means it's going to be exponential, or you need a DP, or you need like something magic like flow or simplex.
Or you just guess. Well, it was just going to be like whichever one's bigger. Which doesn't seem to be right.
Since you're giving different numbers, that's very tricky.
Yeah.
So someone said it's greedy. So why 60? 60, no particular reason.
You could
60 works.
you
You could do something else too.
Yeah, you could do a bigger or smaller number. I think the smallest number you could pick there is like 18 or something.
Yeah. So the idea here is that instead of like, so what you're doing here is like you're going left to right, which they do in the problem, but it's much easier like if you go right to left. Because the problem with going left to right is you don't know how much you'll end up with.
Yeah.
Because future things will affect you.
So give as much as you can.
Yeah, if you give as much as you can, you might as well do
Okay,
it,
this makes
right?
Yeah, this is easy. Okay.
Yeah, so there's a slight, it gets a little messy, but it's not too messy. It's just one thing you might want to like avoid, which is, okay, so like you want to give, let's say we're binary searching, we know the answer is 7.
Sure.
We want to see whether 7 is
yeah.
possible. So can you do 7?
Mm.
So for 100, you don't care, like there's no reason to have more than 7 left over.
Yeah.
So we're going to try and subtract 93.
Sure.
Or 93 is a multiple of 3, but we do the biggest multiple of 3 that we can. Okay, so what's 93 over 3?
31.
1. Okay, so this is plus 31, and this is plus
62.
62. Okay, so after this would end up with 41, and this would end up with 64. So a very natural thing to do would be say we want this to go down to 7.
Why not? Yeah.
So how much do we subtract to make it go down to 7?
32? 34?
So 33?
33?
Okay, you see what the problem here is?
No, what's the problem?
The problem is we're subtracting 33. Which, in one sense, is kind of fine,
Yeah.
because we'll end up with 41. But in reality, when we're doing this in the actual problem, they said we're going left to right. Which means
We don't have
we do this
33.
one first. We only have 10.
We only have 10.
Yeah. So you can
Ah.
so you have to like be careful here.
I see.
But like once you see that, it's pretty obvious. So okay, now you subtract 10.
So it's always
but
going
really
to-
9, because 10 is a
Yeah,
multiple
yeah.
of 3. So you subtract 9.
I see.
So this is
Sure,
plus
sure.
3. This is plus 6.
Yeah.
Then you do this one, and then you subtract. Well, okay, you stop at 2. You run out of space. I don't have a sister H. Good morning, Jitendra. So yeah, that's the solution to problem C. Hopefully that made sense. You binary search the answer, and then you go from right to left, but you have to be careful to never subtract more stones from a pile than you have in the pile. And samples were nice, so that helped us. Yeah, somebody said you can do greedy in this, and I have no idea how. I'm not really sure how people said you can do greedy. It doesn't seem possible, but I don't know. You haven't got any motivation to play for the next one. The next one's the goodbye round. There aren't that many specially named contests in a year. You've got goodbye that year, hello that year. You got the April Fool's contest that year. I guess you got Colin Heroes. I don't know if that counts as special.
Oh.
And you got a couple global rounds. But other than that, I don't know. The goodbye one's got to be pretty special. Okay, so that's A, B, and C. Let's talk about D, I guess. So, did you read D?
Yeah, it's just A, right? But with the probability?
Yeah, and bigger bounds.
Bigger
and
bounds, yeah.
expected value rather than required. Goodbye is free rating. If you're yellow, it is. If you're LGM, might be tricky. Also, like, interestingly, it's only 2 hours. You notice that?
This one?
Yeah, this goodbye contest is only 2 hours.
Yeah.
Which is, like, surprising because usually, I'm pretty sure everybody's together. Right, so,
What does that mean?
like, usually in global rounds or Div 1 plus Div 2,
Really?
it's like either 2.5 or 3 hours.
Oh, yeah.
This one's only 2. So I don't know how they're going to do that, but there you go. Okay, so problem D. Let's bring it up. Robot cleaner revisitation. Yeah, so I wasn't able to code this in time for whatever reason, but I can give you some ideas for it. So you've got this room, and you again have a robot. Maybe we'll just let you see the statement because it's very pretty again. So here you go. Here's like an example. So again, you've got a room and a Roomba. And the Roomba is going to move around the room in the same pattern that he did for A. But in this case, it's not exactly independent because once you consider vacuuming some square, like you don't necessarily 100% vacuum it. There's only a probability, like some percentage, some integer percentage that you'll clean the square. And if you get lucky, then you'll clean the square, but otherwise you might not. So then the question is, what's the expected number of turns in order to clean the square? Obviously, if you do this infinitely long, you'll have an infinitely high chance of cleaning the square, but it's not necessarily guaranteed.
Yeah.
So, yeah, in both of the samples they give us, it's pretty easy because you have a 100% chance of cleaning the square each time. They're both samples that are drawn anyway.
There 100% chance of hitting the square.
Yeah, 100% chance of hitting it. But that's not true in general. And actually, those two samples were the two ones that broke my solution. So, or broke my code anyway. My decision. So, like, one thing you can consider in these problems, which is often very helpful, is if you have some robot, like let's say this is you, you can try taking yourself and rather than bouncing off walls, you just like go forever.
Oh, sure.
So this is known as like the reflection trick. And because like you would bounce off walls, instead you like imagine the walls bounce off you. So you can imagine this is like the grid, and then the grid will be over here. And then if this is the square will get translated to this.
Yeah.
So that's kind of like the idea, and this is a very common idea in lots of problems where you bounce off walls. In like pool table things, it's common. In like Atari, you've got the little pellet that bounces off the wall.
No Pong?
The brick breaker one,
Oh, sure, yeah.
where you like shoot at the bricks and you
Yeah.
gotta, yeah. So it's similar with that. And a lot of times use Chinese remainder theorem with this because, yeah. But I don't think that's required here, because bounds are only up to 10 to the 5th rather than like 10 to the 7th. Include the div1 guys, and my rating graph dives deep into the gray ocean.
Yeah.
I mean, maybe, but maybe not though. Like, if you beat someone who's in div1, then your rating goes up, right? So it shouldn't matter. Mathematically, there shouldn't be any difference. Assuming it's not like a super clear-cut division.
Yeah.
But anyway, yeah, so here is like this idea. So there are like an infinite number of these too. Like you can bounce off this wall and then also this wall, which we do. So this thing gets reflected over, well, I guess there's not enough room to show it, but we'll draw a smaller version here. So you get this, you have a clone here, and then this one is like the same as the original. So if it were here, then it would be here, and then it's here again.
Wait, no, it's...
Oh, JK. It's in this position again.
Yeah.
Yeah. So that's the idea. It would be really nice if we were in the top left corner. Right? That would make things really convenient.
Why?
If we started in the top left, it would just make the math easier.
Because we did it?
Yeah, because like, then once you go width times height times 4 steps, you wind up in the top left corner of another element.
Do you not start? Is there a standard starting spot?
You start somewhere. Like,
yeah,
you start on the blue carpet in the animation.
Yeah.
Oh, you guys can't see the board. Dang it. Sorry. Yeah.
Okay, yeah.
So, it would be nice if we started in the top left corner. So let's try and do that and see what happens if we do. I've got my head chopped off. So what if we like reframe this? Yeah. So let's say we start like here instead. We're gonna like change the frame.
Okay.
Now this would be really annoying if like we ourselves had to bounce off these random positions. But now that we're just going in a straight line, it's like much easier.
Yeah.
The only confusing
This
part
is cool.
is that this trash, it like does weird things.
And it's not, yeah.
But there's still going to be, when we start, there are still 4 positions, right? So we've got this position, this one here, and then we flip them over this axis. So we have this here and this here.
Mm.
And then we have like this bigger square here, which is like the 4 things. But then we have a copy of this over here. Right? And this is just like a stamp, not a reflection. So we'll have these 4, we'll have the same 4 here, and then we'll have the same 4 here, and here.
Yeah, you got to.
And since we start here, we will also be in this position here, because we're going directly along this line.
Okay.
Does that make sense?
Yeah, because we're on the top
checking.
left.
Please zoom in. Okay, we're zoomed in. Hopefully this should be a little bit better.
Can you guys see?
Is the red showing up? It looks decent. Not terrible.
Yeah.
So yeah, so that's the idea. We're going to start in one position and then like reframe the board to be at where we are. So then all we have to do is count in this thing where we go from here to here. We want to see how many times would we clean the carpet.
So does this square matter at all?
This one?
The bottom right? Yeah.
It'll kind of, because this goes like infinitely far. But the key idea is that once we make it to the bottom right, it was the same as when we started.
Yeah. But so
because like this
we're
goes
only
infinitely.
counting from here to here, right?
Yeah, so we're going to go from here to here, and then the next step will be moving to there.
Okay.
That's the idea.
But we don't care about these x's because they're not gonna matter.
Yeah, these x's aren't going to matter.
Okay.
These x's also won't matter. These won't matter either.
Wait, they won't?
No.
Oh, okay.
The path we're going to take is going to be this.
Okay.
Wait, that's not true. Like, okay, yeah, all of these other things do matter. Sorry. Kind of let me step back a bit.
Yeah, okay.
These things matter, but we're going to make a bunch of copies of this and then end up at another square here. So this is only true if this thing is a square.
Oh, sure.
But we can make it like a square by...
So we're gonna keep going until we hit the...
Until we hit the top left again.
Okay, sure.
Yeah. Okay, so how do we make it like a square? So let's look at like a 3x2 example, because that's pretty easy.
Yeah.
So this is 2 wide and 3 tall. And we do this. Then this is going to be 6. And then this will also be 6.
What are the bounds on how big this can be?
Each dimension can go up to 10 to the 5th.
Oh, so you can have a lot.
Yeah, kind of. So in total you can have 10 to the 10-ish, times 4 maybe. But the total number of things within each row is only 10 to the 6th.
Yeah.
The other thing is, within each square, there's only one place that matters.
Only one?
Yeah.
Why isn't it 4?
Or, I guess they're, like, on average it's 1.
Oh, okay.
But I think it's only 1. Maybe it's 4. I don't know. Whatever. There's a constant number, small constant.
Yeah.
So, yeah. So you've got like some things in these squares. So what we're gonna do is like look at all of the x's that matter, and the important thing is like let's say there are 2 here in this square. The ones in this square are gonna have the same x coordinates.
Sure.
So we only have about like 10 to the 5th x's that matter.
Okay.
We also have only 10 to the 5th y's.
Mm-hmm.
So we want to figure out at which times are we at either an x or a y or both. Problem D, yeah. Either an x or a y or both positions that matter. That's the question.
Okay.
Does that make sense?
Yeah.
Which times?
Yeah, this is problem D. Oh yeah, I got it. And
Yeah.
What is the time complexity this going to end up being?
It's going to be either linear or n log n on this 10 to the 5th bound.
Okay.
I'm not sure if you can do it better.
Yeah.
You might be able to with some like fancy math, but fancy math is annoying. So, yeah, so that's the idea. So like, if you imagine walking like this, we know we're gonna end up at this position here.
Yeah. Okay.
So after we end up at this position, the entire thing resets.
Yeah, and it just repeats.
Yeah.
Yeah.
So we're gonna solve this with that part with the math, like the infinite part with math, but figuring out like which positions we hit things that matter in, that's gonna be something we want to do with like just doing it naively.
Yep.
So we know, let's say these are the 4 positions that we hit. These will be the same in every square, but just with offsets. So they'd be like this. So we need to check some x's and some y's. We need to check like this x, this y, or these y's, this y, this y, and then these x's matter.
To see if we hit them?
Yeah, so at each of these x's and these y's, at that time, sorry, the markers kind of died, but at that time, we will clean this square. Because we'll be, like the Roomba will be at either the same x as the square or the same y as the square.
Yeah.
So, we just need to know if there's like an overlap, or like we need to know what time these occur. So yeah, using that we can like figure out how much time passes between when we started and when that happens.
Yeah, that makes sense.
Okay, so then the next idea, the final idea is like the math part. That's the main part. Yeah. So it's like, then how do you do the math? So I'll talk about like the geometric series math just a bit, but you learn about this quite a bit in, I guess your math classes.
Calc 2.
Probably algebra.
Maybe.
Maybe, I don't know. So you've got this thing. So it's like you have to pay this cost with some probability. So you have to pay like S1, like the length of, or we'll call it L1. So this is L1 here, and then this is L2. So L2 times P1 plus L2 times the chance you get there, which is P1 is the chance that you get here. I guess so this is L2 times 1 times just 100% times L2 times P1, where P1 is the chance that you don't clean it after this thing, plus L3 times P1 times P2, etc.
Yeah.
And then you do that for this entire thing. So at the end, what you'll be saying is like times this like Ln plus Ln times P1 times P2 all the way up to Pn minus 1. Yeah, is this legible? Looks probably good enough. So yeah, this is like what this equation works out to. But this whole thing is just like a common ratio. So this is just a geometric series that will repeat for the next thing.
It'll get smaller. Or it starts at 1 here.
Yeah, it starts again. But
Okay,
now this next time, instead of this being a 1, this is going to be this constant. Yeah, so this is a geometric series, so you can plug it into the formula. But basically, the other way of looking at it, if you don't want to use the geometric series, is that you have like the value here is the same as the value here times a constant.
Yeah.
So just like formally, you have like the answer equals some constant, right? The constant that you have to pay here.
Yeah.
Plus some constant constant 2 times the answer. So this variable here is the same as this variable here. And this is not the number 2, this is like some r. So you can solve this with algebra. Does that make sense? Should I actually do it? So you get like ants minus r times ants equals a constant. And then we factor out the answer here, so we get 1 minus r times the answer equals a constant. And then you get the answer equals the constant over 1 minus r. So this is I'm pretty sure this is just what the formula is.
And we're trying to find the constant here.
No, we know the constant.
Oh.
The constant is just, we did it with the for loop. For each of
Yeah,
these
yeah.
parts.
So the hard part of the problem is trying to get this constant.
Yeah, once we get the constant, and we need R2.
Like a second ago.
Okay. Welcome back.
Yeah.
That was problem D. Alright, yeah, so I guess that's it's kind of the end of the stream for today, because we haven't done E. Yeah, it was A, B, C, D. Awesome. Okay. So yeah, I guess thank you guys for watching. I think that's all we've got for today, right?
Yeah.
We could read E and try and solve it live, but I think we're pretty unequipped to do that at this point.
Yeah.
Awesome. Oh, welcome, Carissa. Carissa's here.
Oh, nice.
202. TD pencil. It's yeah. I need to get better batteries or something for this camera,
Should we just
right?
charge it when it's going?
Well, it is charging.
No, the camera.
I have no idea.
Okay.
I don't know. So we gotta figure it out. Anyway, thank you guys for watching. Geothermal's got a solution to problem E, so if you want to check that out, you certainly can. But I guess that's all for us today. Good luck on the global round, not global round, JK. The Universal Goodbye 2021 that's happening tomorrow morning. Yeah. Don't miss it. It's like 2 hours later. Starts about this time. No, JK, 45 minutes ago, but still fun. Will we be doing a stream tomorrow? Probably.
Yeah, probably.
Sounds like the plan. Yep. And then tomorrow evening I'm going back to Seattle, so that'll be the last stream with Thomas in it for a while. Awesome. Okay, sounds good. See you guys. Thanks for watching, and good luck. Have fun.